The reluctance is magnetic circuit is similar to resistance in the electric circuits. The reluctance in the magnetic circuit is equal to resistance in electric circuits, so that the reluctance it can be measured as L upon mu s. L is equal to length of the conductors, S is surface area of the conductors, mu is permeability of the mediums. Permeance is the reciprocal of the reluctance, as conductivity is the reciprocal of resistance. This is mu s upon L. So that here this one it is a electric circuits V I and resistance R. Similarly this one it is a magnetic circuits, a coil it is wound around a metallic ring, so that it is a magnetic circuits. In electric circuits the resistance is EMF is EM upon I, it is EM upon I. In magnetic circuits reluctance it is equal to mmf upon pi, it is equal to Ni upon pi. So that the reluctance of the circuit it is equal to reluctance of the circuit it is equal to the ampere turn upon Weber. Reluctance of the circuit it is equal to ampere turn upon the ampere turn upon the Weber. That is use the reluctance of the magnetic circuit. Reluctance is magnetic circuit is similar to the resistance in the electric circuits. Reluctance is mmf upon pi, it is equal to Ni upon pi. Magnetic boundary conditions. The normal components, a cylinder is placed in a surface placed at the interface between the two mediums 1 and 2 having permeabilities mu1 and mu2, so that closed integral b dot ds is equal to 0 for a closed surface. Closed integral b dot ds it is equal to the top surface, bottom surface and lateral surface. The higher and the height of the cylinder is delta h, at the boundary delta h tends to 0, so that integral lateral b dot ds is equal to 0. In the magnetic flux entering to the cylinder in medium 1 and leaving from the medium in cylinder 2 in medium 2, so that closed into b dot ds is bn1 delta s minus equals 0. So the delta s is the incremental surface area of cylinder at the top and the bottom surface. Bn1 and Bn2 are the normal components of the flux density in medium 1 and 2, so that Bn1 delta s minus Bn2 delta s. Bn1 is equal to Bn2, so the normal components of flux density are continuous at the boundary between the two mediums. Tangential components. A closed path in the form of a rectangle is placed at the interface between the two mediums. Height of the rectangular closed path is delta h, width of the rectangular closed path is delta w. The sides AB and CD are tangential to the boundary between the two mediums. Sides BC and DE are measured to the boundary top to bottom according to the Ampere circuit law. So that closed in A to B S dot dl is equal to I is A to B, B to C, C to D, D to A. Sides BC and the sides DA are normal to the boundary. Are normal to the boundary. At the boundary delta h tends to 0, so that the line integral of h along the path BC and DA is equal to 0, so that A to B only B to A h dot dl is equal to I. So that the I is equal to del cross k dot del w, k is equal to current density, so that the sides EV and DA are tangential to the boundary. At the boundary current is equal to 0, so that H tan 1 delta W minus H tan 2 delta W is equal to 0. The humidity is equation. The direction of H is opposite to the medium, so that H tan 1 is equal to H tan 2. The tangential components of magnetic field intensity are continuous. The tangential components of magnetic field intensity are continuous at the boundary between the two mediums. Now the equations from those boundary conditions, Bn1 is equal to B, normal components of flux density are equal, so that B is equal to mu H is Bn1 is equal to mu 1 Hn1, Bn2 is equal to mu 2 Hn2. Here In1 it is equal to that is Hn1 upon Hn2 is equal to mu 2 upon mu 1 is equal to mu 0 mu r2 upon here mu r2 upon mu 0 1. Here mu 2 and mu 1 are the relative permittivities of the medium 1 and 2 respectively. Tangential components H tan 1 is equal to H tan 2. Therefore, H is equal to the B is equal to mu H. So H tan 1 is equal to B tan 1 upon mu. H tan 2 B tan 2 upon mu 2. B tan 1 upon mu 1 is B tan 2 upon mu 2 is equal to B tan 1 mu 2 by mu 1 mu 0 upon mu r2. Consider an interface in the YZ plane. The region x less than 0 medium 1 with mu r1 4. Magnetic field intensity H is equal to ampere per meter. The region x greater than 0 is medium 2 with mu r2 is equal to 6. Find H2 in medium 2 and the angle made by H2 with the normal to the interface. Here it is the alpha currents in the medium 1 and the medium 2. At the boundary between the two magnetic materials having different permeabilities, normal component of the magnetic flux density. The normal component at the boundary between the two magnetic materials having different permeabilities, the normal component of magnetic flux density is equal to closed integral by at the boundary between the two magnetic materials having different permeabilities, normal component of magnetic flux density are equal. Bn1 and Bn2. Tangential components of magnetic field intensity are also equal. Tangent H tan 1 H tan. H1 is equal to 4x plus 3y minus 6z. The normal to the interface is along x directions. Therefore, H tan 1 plus Hn1, so that H tan 1 3y minus 6z. Hn1 is 4x ampere per meters, because it is the normal to the directions. It is a plane. The region x less than 0 is medium 1. That is the reason. The region x greater than medium 2 with mu r2 is equal to 6. So that here the 2 it is normal to the it is along the x directions. If the H tan 2 is equal to H tan 1 is equal to 3y minus 6z ampere per meter, Bn1 is equal to Bn2, mu 1 Hn1 is equal to mu 2 Hn2. 1 upon Hn2 is mu 2 by mu 1, it is mu r2 is mu r by Hn1 by Hn2, it is equal to 6 by 4.5, Hn2 4.5 by 6 into bracket of Hn1 is equal to 4x. So that H2 is equal to H tan 2 plus H2. From that one, the H2 is equal to 3ay minus 6az plus 3az. So H2 is equal to 3x plus 3ay minus 6az. The angle made by H2 with normal to the interface. H2 dot Ax is equal to modulus of H2 modulus of Ax cos alpha 2 plus 3 minus 6az. Square root of 3 square plus 3 square minus 6 square into bracket of Ax dot Ax is equal to 17.34 into cos of alpha 2. So that cos of alpha 2 is equal to 3 upon 7.34 is equal to 0.0408. 2 is equal to cos inverse of 60. But 3.4 alpha 2 is equal to cos inverse of 0.408. Alpha 2 is 65.92 degrees. Inductance of a magnetic metals. A coil of N turns carrying current I, producing a flux around it. The flux linked with the coil. The flux linked with the coil having the n turns is equal to n pi. The flux linked with the coil is directly proportional to the current flowing through it, so that the inductance, the flux linked with the coil is directly proportional to the current flowing through it. The ratio of flux to the current flowing through the coil is known as the inductance. Inductance is equal to flux linkage upon total current is equal to L is equal to N pi by I. Because the flux linked with the coil is directly proportional to the current flowing through it, the ratio of the flux linkage to the current flowing through it, the ratio of the flux linked with the coil to the current flowing through the coil is known as the inductance. Flux linkage upon total current L is N pi by I. Inductance of a solenoid. A solenoid of length L here carrying current I and having N turns. The magnetic field density, the magnetic flux density within the solenoid is B is equal to mu Ni upon L. The flux linked with the solenoid is having N turns is equal to flux linked is equal to N pi. Magnetic flux pi is equal to Ba. Pi is equal to mu Ni upon L into bracket of A. Because here this one it is the magnetic flux density within the solenoid, mu Ni upon L. Flux linkage is equal to N pi is equal to N into bracket mu Ni upon L into A. Flux linkage is equal to mu N square I upon L into A. Inductance L is equal to total flux linkage upon total current. L is equal to mu N square I upon L into bracket 5 into A. L is equal to mu N square A upon L. Mu N square A upon L, that is inductance of a solenoid. N is permeability, mu is permeability, N number of turns, A area, L is the length of the solenoid. Inductance of a toroidal. The toroidal ring of the mean radius R carrying a current I and having number of turns is equal to N. This one it is a toroidal coil having the mean radius it is R and a coil it is a coil is present around the a magnetic coil is wound around that ring and it is carrying a current I. The magnetic flux density of the toroidal ring is B is equal to mu Ni upon 2 pi R. The total flux linked with the toroidal coil having N turns is total flux linkage is equal to N pi. Magnetic flux pi is equal to Ba. Pi is equal to Uni upon 2 pi R. Uni upon 2 pi is magnetic flux pi is equal to Ba. Pi is equal to mu Ni upon 2 pi R into A. Flux linkage is N pi is equal to N into bracket of mu Ni upon 2 pi R into A. Mu N square I upon 2 pi R into A. Inductance L is equal to total flux linkage upon total current. So that the L is equal to mu N square I upon 2 pi R into I into A. Mu L is equal to mu N square A upon 2 pi R. A is area, R is mean radius of the toroidal ring. Two wires carrying current in the same direction of 3 ampere and 6 ampere are placed with their axis 5 cm apart. Free space permeability is 4.10 raised to minus 7. Calculate the force between them in Newton per meter. I1 is equal to 2 conductors carrying current 3 ampere and the 6 amperes and the currents are in the same directions. I1 is equal to 6 ampere, D is equal to 5 cm 5 10 raised to minus 2, mu naught is 4.10 raised to minus 1. The force between the two conductors carrying current in the same direction is F is mu naught I1 I2 L upon 2 pi D. F is equal to 4.10 raised to minus 7, 3 into 6 into L upon 2.5 into 10 raised to minus 2. F upon L 4.10 raised to minus 7, 2 pi into 5 into raised to minus 7.2 into 10 raised to minus 5 Newton per meters. Because the force between them, calculate the force between them in Newton per meter length, F upon L, and 2 into 10 raised to minus 5 Newton per meters. Because F is mu naught I1 I2 L upon 2 pi D. L is length of the conductors, D is the distance of separation between the two conductors. I1 and I2 are the currents flowing through the two conductors. Mu naught is free space permeability. A coil of 500 turns is wound on a solenoid. Wound on a closed iron ring. Wound on a closed iron ring of mean radius 10 cm and cross-sectional area of 3 cm square. Find the self-inductance of the winding if the relative permeability of iron is 800. N, it is a toroidal ring, is that is N is equal to 500, R is equal to 10 cm is equal to 10 into 10 raised to minus 2, 3 into 10 raised to minus 6, 3 into 10 raised to minus 4 meters square. Mu r is equal to 800 L. The self-inductance of the toroidal ring is L is mu n square A upon 2 pi r. Mu is equal to mu naught mu r 4 minus 7 into 800. L is equal to mu naught, L is equal to mu n square A, mu n square A upon 2 pi r. Mu is 4 pi 10 raised to minus 7 into 800 into 500 square into 3 into 10 raised to minus 4, 2 pi into 10 into 10 raised to minus 2. L is equal to 0.12 Henry. L is equal to mu n square A upon 2 pi r. Mu n square A upon 2, mu n square A upon 2 pi r. L is equal to 0.12 Henry for the that is the inductance of a toroidal ring. That is the self-inductance of the toroidal ring is equal to mu n square A upon 2 pi r. A is area of cross section, is number of turns those are wounded on that toroidal ring. R is the mean radius and mu it is permeability. So that from that we will getting L is equal to 0.12 Henry. Calculate the inductance of a solenoid of 200 turns wound tightly on a cylindrical tube of 6 cm diameter. The length of the tube is 60 cm and the solenoid is in air. Solution: N is equal to 200 turns and L is equal to 60 cm, 60 into 10 raised to minus 2. D is equal to 6 cm, 6 into 10 raised to minus 2 meters. So that R is equal to D by 2 is equal to 3 raised to minus 2 meters. Solenoid is wound on a cylindrical tube of area of cylinder. It is A is equal to pi r square. So that A is equal to pi into 3 into 10 raised to minus 2 square. A is equal to 28.27 10 raised to minus 4 meters. Mu is equal to mu naught, because air, solenoid is in air, mu naught 4 into 10 raised to minus 7. The inductance of solenoid is L is equal to mu n square A upon L. So that here this equation already we have determined, that is the inductance of a solenoid is equal to mu n square A upon L. L is equal to 4 pi 10 raised to minus 7 into 200 square into 28.27 into 10 raised to minus 4 upon L 60 into 10 raised to minus 2. So that the inductance of a solenoid L is equal to 0.236 millihenry.